What's up, party people? So we're gonna get right into it. So first of all, good morning. If you're watching this video, thank you for taking the time to look at the lesson to get the information that you're gonna need for Unit 5, Lesson 8. Now, this, as you can see, the title of this lesson is Features of Graphs and the Average Rate of Change. And so with this lesson, we are going to cover activities 1 through 5, actually. It may be a two-part video, so if it is a two-part video, I'll send both parts and I'll have these connected in the Canvas and whatnot. But let's go ahead and get right into the information. Let me get the pages that I need set up. So we're going to, let's see, let's do the first 3 together first. And then if we need to do a separate video, we'll do that. So if you can see my screen, you're watching this live, put a 1 in the chat. If you're watching this on the replay, then definitely post a comment or something in the chat. If you have any questions, feel free at any time to post comments in the chat. I'll get notifications for them and I can answer them. So as you can see, we're on page 79 and there is a picture and it gives a description of this graph that we showed. Now notice there are 2 different graphs in the same one. It says a toy rocket and a drone were launched at the same time. Here are the graphs that represent the heights of 2 objects as a function of time since they were launched. So notice you have on the independent axis or the x-axis, you have the time measured in seconds. And then on the dependent axis or the y-axis, you have the height measured in meters. Now, notice it says the height is measured in meters above the ground and the time is measured in seconds, okay? So I want you to take some time real quick and think about the mathematical questions that you would ask about this. You can think about those out loud. You can post those in the chat. You can write those in your workbook and ask me those in the classroom. Now, when we look at this, let's see what it's asking us to do with this. So notice it says, analyze the graphs and describe as precisely as you can what's happening with each object. Your description should be complete and precise enough that someone who is not looking at the graph could visualize how the objects were behaving. This is very, very important because there's different pivotal points in the 2 paths of these objects that if you can describe them, then you can actually do the mathematics on paper and you can answer questions. So I want you to think out loud with terms like these sentence starters that say, it looks like, or I noticed that, or blank represents blank, or what does this part of the graph mean? So there's thoughts as well as there's questions that you want to ask yourself about these 2, this graph that has the paths of these 2 different objects. Notice one is a rocket. So you want to think about things like, it looks like the path of R models the rocket, and things like, it looks like the path D represents the drone. Okay, so this is actually what's going on. And so you may want to ask yourself questions such as, what does this part mean? So for example, when I say, what does this part mean? You may say, okay, well, what does this flat part mean right there? Or what does this mean here when it goes up at a certain point and then starts to come back down? So these are questions that you want to think about while you're looking at this, okay? So now what I would say is, for example, so we're going to describe this as precisely as we can. And when we describe this, we want to see, okay, so for example, I noticed the way I described it is that the path of R, which appears to be the rocket, notice it was launched at a point that was 25 meters above the ground. And for the first 2 seconds, the rocket's path increased. So it went higher in the air until it reached a maximum point after 2 seconds of about 45 meters in the air. So we know the highest point of this rocket, it took 2 seconds to get there and it reached a maximum height of 45 meters in the sky, right? Then we noticed after 2 seconds that this rocket began to go back down, right? So that, and then as it goes back down, of course, it's approaching the ground. And if we think about a rocket, it launches up in the air and it comes back down, right? And so then we can see that after 5 seconds, the rocket has hit the ground. Okay. So this rocket was in the air 5 seconds. It was launched 25 meters above the ground. It reached a maximum point after 2 seconds of 45 meters. And after 5 seconds, the rocket hit the ground. So that's one thing we want to think about, right? Now, when we look at the path of the drone, when you think about in real life what a drone does, a drone starts at the ground. So that would be this point right here, and I'm going to use a different color red. So this drone starts on the ground, and this drone started to go into the sky for the first 2 seconds, and it reached a maximum height of 20 meters above the ground. In this 20 meters, this drone is basically hovering, right? So it's hovering in this flat part, and it hovered. It looks like it started hovering at 2 seconds, and then it hovered until 5 seconds at that maximum height of 20 meters above the ground. Then we notice after 5 seconds, this drone starts to come back to the ground, and it reaches the ground at 7 seconds. Okay. So once again, this drone started on the ground, and it took 2 seconds to reach a maximum height of 20 meters. It hovered above the ground at that same height of 20 meters for 3 seconds. And once it got to 5 seconds, now the drone is coming back down to the ground. It took another 2 seconds for this drone to come back to the ground. So we can tell that the drone was in the sky for 7 seconds. The rocket was in the sky for 5 seconds. So this is activity 1. These are different key features of the graph. Now, when I look at these key features, I kind of talked about them there, but we'll go on to part 2. It says, what parts or features of the graph show important information about the object's movement? So for example, let's go back with the green for the rocket. This maximum point was an important part, okay? So that maximum point was important. Also, this vertical intercept on the y-axis tells us how high the rocket actually was when it was launched. And then we have this minimum point, right, where the rocket hits the ground. Those are 3 key pieces of this rocket's path, okay? Now, if we clear that out and we go and look at the drone, there are some key pieces of this drone's path. We know right there, that's where the drone was on the ground. We know this is another key part where this drone begins to hover at 20 meters in the sky. We know another piece right here where the drone, after 5 seconds, it's getting ready to go back to the ground. And then we have this part right here at 7 seconds where the drone actually lands on the ground. So those are the key pieces in this graph, and looking at the features of the graph and what is happening with the path of both of these objects. Okay, let's go over to activity 2. Now, activity 2 looks really heavy, but you'll see that there is something on this graph or on this picture in this scenario that is missing in your workbook. So I want you to pay attention to this piece right here. H of t equals 45. I'm noticing that it's not listed in the workbook, but if you're watching this video, I want you to write that at the bottom of the list under H of t equals 80. So we want to talk about in these next few questions. So this is a bungee jump. And if you're familiar with bungee jumping, basically somebody jumps off of a bridge. They have this bungee cord attached to them. And when they first jump, they go down, the bungee cord stretches all the way out, and that person begins to bounce up and down. And as you can see, the path of this graph, they go down. So this is the maximum, or I'm sorry, the minimum point. And then they jump back up, not as high as they originally were, and they keep bouncing back up and down over time, right? And so if you can picture this, I want you, if you can't picture this, or if you don't know what this looks like, I want you to go to Google or somewhere on YouTube, and I want you to look up a video of someone bungee jumping, okay? Now, let's read the situation. It says, in a bungee jump, the height of the jumper Okay, so the height of the jumper is a function of time since the jump begins. The function h, so this is the name of the function. That's why we have the h's out here, okay? So the function h defines the height in meters of a jumper above the river t seconds since leaving the platform, okay? So what it's saying is height is a function of time, okay? So here's a graph of function h followed by 5 expressions or equations and 5 graphical features. So as you can see, there's a table, which I'll show you next. There's a table here that talks about different pieces of this graph. And we want to match the different expressions or equations with the features of the graph. Notice that these expressions and equations are written in function notation, okay? So let's get right into the table that they have on the next sheet, okay? So notice it says, we're gonna match each description to the corresponding expression or equation and to a feature on the graph. One expression or equation does not have a matching verbal description. So that's down in number 5, right? We're gonna have to figure out what verbal description goes there. And it says its corresponding graphing feature is also not shown on the graph. Interpret the expression or equation in terms of the jump and in terms of the graph or the function, and we want to record that information in this table. So we're going to start with number 1. It says the greatest height that the jumper is from the river. Well, when we think about the path, they're starting out from this platform, right? So that's the highest point. So this is h of t equals 80, okay? And the reason that is simply because if you look in the if you look at the graph, notice that the y-intercept of the graph starts at where the height is 80, okay? And so the feature that goes with is the vertical intercept, okay? Also known as the y-intercept, okay? Number 2, it says the lowest point that the jumper reached in the entire jump. So after that initial jump, they're going to go to the lowest point because that's when the bungee cord is going to stretch out all the way. But if you look at the graph, I'm going to swing back. If you look at the graph, that lowest point is right here, okay? And notice it's approximately after 4 seconds. So you're going to see me keep going back and forth between the graph and these descriptions. So this is going to be h of 4, okay? Notice the expression doesn't tell you how high it is at that point, but we know that is the height after 4 seconds, okay? So this is the first dip in the graph, okay? First dip in the graph, okay? Then notice we go to part 3. It says the time at which the jumper reached the highest point after the first bounce, okay? So when we go here, let's clear this out. I cleared that out. Actually, I didn't mean to clear the entire thing out, but I want to erase a little bit, okay? So let's use a different color, okay? So here, it's right there. And why is it not writing? So boom, right there. That's the highest point after the first dip, okay? So now when we look at that, if we go back to the table, this is going to actually be h of t, okay? H of t equals 45. That's the one that's missing in your workbook. So if you didn't write that down, you want to write this down. It's not listed in your workbook, okay? So this is the first peak in the graph, okay? This is the first peak, okay? So then now it says the height from which the jumper was jumping, okay? Well, when the jumper first jumped, it's going to start at the highest point, right? So the time, they haven't jumped yet. So no time has passed since they have jumped. So we're going to say this is going to be h of 0, okay? And this is the, in this case, This is also the vertical intercept. Okay, this is also the vertical intercept. All right, and then last but not least, we haven't used this equation right here. H of t equals 0. Okay, well, when h of t equals 0, so when the height is 0, they're back on the x-axis, right? So this is what we call the horizontal intercept, or the x-intercept. Once again, the horizontal intercept or the x-intercept. Well, how do we describe that? And we describe that as the time it takes for the jumper to hit the water, or the river, to hit the water. Okay, so look at this, compare it with the different points on the graph, such as, let's clear this out so you can see this again, and then I want to erase this so that you can see these different points on the graph. Okay, so we have the initial point where they jump from. We have, it's not shown on here where they hit the water, so this is the lowest point, this is the highest point after the first dip, and then notice every time we got lows and highs, okay? So hopefully this helps. Turn back, pause the video, rewind it, and do what you need to do to get a clearer understanding of that, okay? Now let's move on to activity 3. Activity 3, many of you are going to think about it one way, but we're going to talk about it in terms of rate of change. It says here are the recorded temperatures of 3 different times on a winter evening. Tyler says that the temperature dropped faster between 4 and 6 p.m. May says that the temperature dropped faster between 6 p.m. and 10 p.m. Who do you agree with, and explain your reasoning? Now, we're going to see in this that if we go with Tyler first, between 4 p.m. and 6 p.m., the temperature goes from 25 degrees to 17 degrees Fahrenheit, okay? So that's a change in -8 degrees Fahrenheit between 4 p.m. and 6 p.m., okay? Once again, between 4 p.m. and 6 p.m., the temperature decreased by 8 degrees, so that's why we have a -8. Now, if we go to a different color and we look at between 6 p.m. and 10 p.m., notice the temperature goes from 17 degrees to 8 degrees, okay? And so if we take 17 degrees and we drop it down to 8 degrees, and let me make sure actually it says 17 on here, but it actually should be 18. I apologize for that. That is a mistake in the book, but nevertheless, we'll work with it. So this should be 18 degrees, okay? So once again, 6 p.m. is 18 degrees, okay? So the information in your workbook looks a little different from this slide, all right? So notice if we go from 18 degrees to 8 degrees, we have a drop of 10 degrees Fahrenheit. Well, how did you get that, Mr. Harris? We simply took the temperature at 10 p.m., which was 18 degrees, and 6 p.m. at 18 degrees, and then 10 p.m. at 8 degrees, and 18 minus 8 equals 10 degrees Fahrenheit. Notice that is a -10 because we are talking about the drop in the degrees. So if you look at it just on surface level, you might say, well, I agree with May because she says that the temperature dropped faster between 6 p.m. and 10 p.m. Okay, so notice a couple different things. From 4 p.m. to 6 p.m., it's a 2-hour window. From 6 p.m. to 10 p.m., it's a 4-hour window. And we're going to go into more details in this on the next question, okay? So when I look at this, let's see what the question is actually asking, okay? So the question says, or actually, this is what it is on activity 3. Activity 4 goes into more details, okay? So I'm going to stop sharing for a second, and then I'm going to pull up the other slides so that we can begin talking about this. So now activity 4, we're on page 83 now. 83, it says, how did the temperature change between 4 p.m. and 10 p.m.? How much did it fall? We kind of just talked about that. And now it says, can we tell how fast or at what rate the temperature is falling? If not, why or why not? Okay. So we're going to come back to this. We're not going to answer this just now. Well, we can. It's because it's kind of connected. So between 4 p.m., the temperature was at 25 degrees, and at 10 p.m., the temperature is at 8 degrees. So how much did it fall? If it went from 25 degrees to 8 degrees, then we can simply say 25 degrees minus 8 degrees equals roughly 17 degrees. Now, I'm noticing that as I do this live, that is why the previous slide showed 17, but the numbers are slightly different in this table. So we'll work with it, okay? I want to look at this. So it fell 17 degrees, and it says, can we tell how fast or at what rate the temperature is falling, okay? Now, when we look at this, we can tell what rate, and a rate being how much did it fall per hour, okay? So we want to know how much did it fall per hour, okay? Now, when I look at this also, here's now a scatter plot with all the points of the temperatures since noon, okay? So when I look at the description of this, we can talk about notices and wonders, but I don't want to spend all the time on that. It says, now we have a table that goes along with this graph, and it's a scatter plot. So the table and graph shows a more complete picture of the temperature changes on the same winter day. The function t, notice that's the name of the function. Function t gives the temperature in degrees Fahrenheit, h hours since noon, okay? So here, this is 2 hours after noon, so that's 2 p.m., 4 p.m., 6 p.m., 8 p.m., so on and so forth, okay? So when I look at something like this, I can tell where the temperature was at different points in the day after noon. Excuse me. Now, it says the table shows a graph, more complete picture. I won't read that again. So we want to find the average rate of change for the following intervals, okay? So between noon and 1 p.m. Well, at noon, notice the temperature is 18 degrees, okay? Because it's 0 hours since noon. So this is the ordered pair. Noon is going to be 0, 18, okay? And then, yeah, because the temperature is 0 degrees. And so then now we're going to say 1. So 1 p.m. is 1 hour. So that's the time, X. And at 1 p.m., the temperature is roughly 19 degrees, okay? So 19 degrees. So we can take here and say F of 0 minus F of 1, and find the rate by saying, well, how much time passed, okay? So it goes from 0 to 1. Well, F of 0, as we can see, is 18, and F of 1 is 19, and then 0 minus 1 on the bottom, right? So we're really just using the slope formula. All right, so 18 minus 19 is -1, and 0 minus 1 is -1. And if we simplify that, -1 divided by -1 is 1 degree. So the rate of change between noon and 1 p.m. is 1 degree per hour. Notice this is an increase. The temperature goes up. And as you can see, we look for the point, it goes up from between 0 and 1 p.m. or noon and 1 p.m. We're going to do the same thing for part B between noon and 4 p.m. Okay, so let's erase this because I don't want to scatter out this information. I don't want to confuse you all. All right, so when we look at the ordered pair for noon, it's still here noon. We have f of 0, which is also, let's do it like this. Let's draw it as an ordered pair. Okay, well, then now let's do it like this, function notation. So we have f of 0, and then we have f of 4. Okay, so if we want to find the rate, we're going to simply say f of 0. We can say f of 4 minus f of 0, or we can say f of 0 minus f of 4. Okay, so let's do f of 0 minus f of 4, and then over, let's look at how much time is passing, 0 minus 4. So what was the temperature at noon? Well, we see on the graph that the temperature at noon was still 18 degrees. That's this point right here, okay? I don't know why it erased everything that I had. I just wanted to erase this part, okay? So here, f of 0 at noon, the temperature is 18 degrees. So we're going to say 18 minus, now what is the temperature after 4 hours? Way up here, this point. So that looks like 22, 24, 25 degrees, okay? So 25 degrees, and then over from 0 to 4, okay? So 18 minus 25 is -7, and then 0 minus 4 is -4. So it's 7 over 4, which is about 1.75 degrees, okay? So what this is saying is the rate of change between noon and 4 p.m., the temperature increased by 1.75 degrees per hour, okay? So that's a rate of change. And then now we look at this, and you can do these. Let me say this. You can start with f of 4 minus f of 0, right? It's still going to give you the same number. So let's look at that real quick. So if I do up here f of 4 minus f of 0, then I just switch the 4 and the 0, 4 minus 0. Well, we said f of 4 is 25, f of 0 is 18, and then over 4 minus 0, still get the same numbers. It's simply 7 over 4, which is still 1.75. So I just want to clarify that, okay? Now let's look at the time between noon and midnight. Once again, noon is going to be f of 0, and midnight is f of 12, because that's 12 hours after noon. And that is if we write this in slope form, we're going to have f of 0 minus f of 12 over 0 minus 12. We could also write it like this. Don't be confused. F of 12 minus f of 0, and we put that over 12 minus 0, okay? So what is f of 0? We said f of 0 is 18 degrees, okay? F of 0 is 18 degrees, and f of 12 is, boom, so that was f of 0 here on the y-axis. F of 12 is 7 degrees, okay? So 7 degrees, okay? Now, remember, these numbers are slightly off because that is a misidentification between the workbook and these slides, which I know next time before I use these slides to look over that. Well, 18 minus 7 is 11, and 0 minus 12 is -12, okay? So when we do that, if we want to write it in decimal form, then the decimal form of that is, it's a negative number, but the decimal form of that is, let me find my handy dandy calculator to save time. So 11 divided by 12 is roughly, it's a decrease, so it's negative 0.92. It's 0.9166, but we're gonna round that off. 0.92 degrees per hour. Okay. So what this is saying is that the temperature is decreasing by 0.92 degrees per hour. Okay, so the lesson here is if we're trying to find the average rate of change between two intervals on the graph, for example, if I wanted to find the average rate of change between 4 p.m. and 8 p.m., I'm going to take f of 4, which is 25, and I'm going to take f of 8, which is 11, and I can find the average rate of change between 4 p.m. and 8 p.m. by saying, I can do it two ways. I can say f of 4 minus f of 8 over 4 minus 8, because that's the time of the intervals. Or I can switch it and I can say f of 8 minus f of 4, and then over 8 minus 4. If we do the numbers, they'll end up being the same. F of 4 is 25, f of 8 is 11, and then 4 minus 8 is negative 4. We simplified this, and it looks like it's 14 over 4. It's negative, and we simplified that, and it's approximately 2.5, actually 3. So it's a decrease of 3.5 degrees per hour in that interval. We can do the same thing up here. F of 8 is 11, f of 4 is 25, and then 8 minus 4 is 4. 11 minus 25 is negative 14 over 4, and it still equals approximately, or it's not approximately, it's exactly 3.5 degrees per hour. And that is a decrease because it is a negative number. All right, so that's activity 4. Last but not least, in this piece, it says, remember May and Tyler's disagreement. Use the average rate of change to show how much time, or to show which time period between 4 p.m. and 6 p.m. or 6 p.m. to 10 p.m. experience the fastest temperature drop. So when I look at 4 p.m. to 6 p.m., so we're going to say f of 4 minus f of 6 over 4 minus 6. Well, the temperature at 4 p.m. is 25 degrees. F of 6 p.m. is 17 degrees, it looks like. And then 4 minus 6, okay? 25 minus 17 is 8, and 4 minus 6 is negative 2. So this is approximately a temperature drop of 4 degrees per hour. If we look at May's thought process between 6 p.m. to 10 p.m., we're going to say f of 6 minus f of 10 over 6 minus 10, okay? So what was the temperature at 6 p.m.? We said 17 degrees. And at 10 p.m., it is 8 degrees over 6 minus 10, okay? So this gives me 17 minus 8 is 9, and 6 minus 10 is negative 4. So it is a decrease in temperature, and it's 2.25 degrees, okay? So between 6 p.m. and 10 p.m., the temperature dropped 2.25 degrees per hour. Between 4 p.m. and 6 degrees, p.m. and 6 p.m., the temperature dropped 4 degrees per hour. So which one is dropping faster? We're going to go with, let's do it in red. We're going to go with, because the mathematics shows us that the temperature dropped faster between 4 p.m. and 6 p.m. So we can go with Tyler, okay? So this is another example of what's going on in this debate. Now, last but not least, we're talking about activity 5, okay? And activity 5 is a little different because it's the same thing, but just in a different way, okay? Activity 5 says that, give me just a second, you all. Here we go. So activity 5 says the graphs show the population populations of California and Texas over time. Estimate the average rate of change in the population in each state between 1970 and 2010. Show your reasoning. Okay, so 1970 is here for California because the solid blue line is California. And as a matter of fact, let's do that in blue. Okay, so 1970 for California is there. 1970 for Texas is right here. All right, and then 2010 for California, for Texas is here, and for California it is here. All right, so let's talk about the average rate of change, right? So when we estimate that, notice for California, the population goes from 20 million, okay, so from 20 million to about roughly 30, I'd say 39 million. Let's just say 39 million. And that is over from 1970 to 2010, that's 40 years. Okay, so if we do estimation 20 million and 30 million, so 20 million is roughly half of 39 million. If we round it, it's going to be approximately 40 million, right? So we can say that the population increased basically about 500,000 each year. Okay, and these are estimations. We're not doing exact numbers here because I want you to see. Notice in the numerator of this, we talk about the change in population, which is the Y value or dependent variable. And in the denominator, we have the 40-year change, which is the independent variable, right? And remember, with slope, it's still Y over X, okay? Now, if we do the same thing for Texas, right? So in Texas, it starts out at roughly 11 million in 1970, and it's roughly 20, I'm going to say about 25 million in 2010. And of course, we have a change of 40 years. Okay. So when I think about 11 million out of 11 million out of 39 or 25 million, it's a little more than half. So let's do some numbers. Let's do some calculations. Let's see what 11 out of 25 is. And 11 out of 25 is roughly roughly 44.44. So about 45, less than 500,000, which we can make that as a fraction. But we're just going to say roughly 0.44 million each year. Okay. And for the sake of time, I'm not doing the exact numbers because it says estimate. Okay. So that's why I'm using these numbers. Okay. And this is an increase because this is a positive number. Okay. Notice that in this case, it is changing. It says part B. What does the rate of change mean? Okay. What this means is here, the population increases by 0.44 million each year. And in California, it's saying that the population increases by about 500,000. So if we look at numbers, for Texas, it would be about 440 million. And for California, it would be about 500 million. So let's just say 400. Let's do the numbers here. So about 500 million. Okay. No, I'm sorry. That's not the right number because it's 500,000, right? So yeah, that is about 500,000 each year. Okay. And this right here is about 440,000. Let's do the colors correctly so you all can U5L8. So this is about 440,000 population increase each year, okay? So that's what that is saying. The population is increasing, but notice we're still using the same, we're just estimating this time. We're taking F of 1970 here, and then F of 2010, and we're putting that change over the change in years. Notice this is a 40-year difference, okay? And the same thing here, we're taking F of 1970 for Texas and F of 2010 for Texas, and it's still about 40 years in change, okay? We'll go in more details into this. If you have any questions, please stop, pause, rewind this video. Share this with a friend. If you got a friend that's not doing their work or they're struggling with their work, talk about it. Have a conversation. Post in the comments if you have different questions, any thoughts. Like, share, and subscribe to the channel. I'll continue showing these lessons because I want you all to be able to access them outside of the classroom. Hopefully, this has been very helpful to you all. Continue to put in the work, and it's going to pay off in the long run. Remember, good leaders ask great questions. So if you don't understand something in this video, please do me a favor. Put a question in the comment. Or send me a question in Canvas. Write some notes and ask some questions right down in your workbook, and we'll get those questions answered for you. Thank you for your time. Thank you for watching.